Hey guys, welcome to our Math 112 lecture for section 6.3. So we're going to talk about sine and cosine functions. Now last class we talked specifically about all the trig functions on right triangles. But this time we're going to talk about sine and cosine functions in a more general sense. And so to do that, we're going to always be talking about these angles in standard position. So as it says, let theta be any angle in standard position. Right, so that's an important thing here, that this is in standard position. We'll use a highlighter. Let's highlight. Standard position. Okay, and point xy is lying on the angle's terminal side, and then r is its radius. So let's get a little bit of a drawing or description of what this looks like. Okay, so so we've got our good old x and our y. Okay, we have some angle theta. Okay, so what we have here is that we have some point on the terminal side. Okay, and from that we can create. Actually, let me do this. From that point, we can create this kind of right triangle. Okay, and the distance here is y, because we think about the coordinate point of this, right? It's y. This distance here is x, and then this is our radius. And so what's really cool is by using this, we can actually create all of our trig functions based on these x, y, and r values. And so we get that sine of theta, since this is theta here, right? We don't really have an opposite and hypotenuse and stuff like that, but we can kind of think about using this angle here. And so sine is y over r. And if we have cosine of theta, that's going to be x over r. And then tangent of theta is going to be y over x. And then similarly, right, we can, if we know what sine is, then cosecant is just the flip of that, so it's r over y. Secant of theta is r over x, and cotangent of theta is x over y. Now, for all of these here, we have the condition that either y does not equal 0 or x does not equal 0, depending on what the denominator is. So for secant, x cannot be 0. For cosecant or cotangent, y cannot be 0. And that reason should be fairly straightforward. And obviously with tangent as well, x cannot be 0. Now you may be asking, well, what if x is 0? Or what if y is 0? Well, then we would say that these trig functions are undefined for that specific angle. And it's pretty straightforward there, right? So it makes it really nice. So let's suppose a robotic hand is located at the point 10, -6, where all the units are in inches. Okay, so what we're going to do here is we're going to use these kind of nice standard position ideas to help us out. Now, the kind of missing piece here that should be in this question is that we want to assume that the base of the arm, the kind of origin of the arm, is at the origin. So it's a standard angle kind of thing. So we've got a robotic hand, it swings around the origin, and that's how we go. So let's first get a little drawing in here for us. So 10, -6 is going to be somewhere about here. So this is the point 10, -6. So if we make an angle out of that, how long is the arm? Well, how in the world are we supposed to figure that out? Except, wait, let's make this into a right triangle. Now let me just separate this right triangle from our axes. And if I do that, okay, we get this nice right triangle like this, okay, where this distance here is 10. And now, even though the y value is -6, this isn't a distance of -6. We'd still say it's a distance of 6. Although it doesn't really matter what we're going to do mathematically speaking, because it's going to get squared and become positive. But we can use the Pythagorean theorem to find this radius, or the distance of the arm, the length of the arm. And so we just simply have 10 squared plus 6 squared, and that is going to equal r squared. And so we can just use our calculators to solve this out pretty simply. And we get that our radius is equal to the square root of 100 plus 36, which is about 11.66 inches. So the length of our arm is about 11.66 inches. Pretty cool. So now if we say let alpha satisfy that 0 degrees is less than or equal to alpha, which is less than 360 degrees, representing the angle between the positive x-axis and the robotic arm, find sine of alpha and cosine of alpha. So what this is saying, what this part here is saying, is simply that our angle alpha we're considering is a positive angle inside one rotation. So we're not going all the way around and then going a little more, or anything like that. So if we go back to our drawing, this would be our angle alpha. Okay. So what do we do? Well, we just need to find our sine and cosine of that angle. So sine of alpha is equal to, well, if we come back here, this angle that we've got, alpha, is in standard position. So sine is just y over r. And sine of this alpha, so our y value is -6, and our r is approximately 11.66. Okay. Now, if you wanted to, you could keep that as the square root of 136, which is actually really great. Let's do that. And just in case you wanted to be a little more precise, let's be a little more precise up here. So this is equal to the square root of 136, which is approximately 11.66 inches. So we have an exact solution and an approximate solution. So let's use the exact in our calculations, because that's always better to do. And then from here, we can then get an approximate value that this is -0.514. Okay, what about cosine of alpha? Well, cosine is just the x over the radius. So this is just 10 over square root of 136, which is approximately 0.85, 7. So that's really easy, right? I mean, with this, we had this location of this point. So we found the length of the arm, assuming that it's, base this, or it starts at the origin. And then using a positive angle in standard position, we can find its sine and cosine values using those coordinates and the length of the arm. Cool. Now we have here, let beta satisfy that -360 degrees is less than or equal to beta is less than 0 degrees. So what is this really saying to me? This is really just saying that we have an angle that is negative, but within one rotation. So if we come back to our drawing, that would mean that this angle here is our beta. Okay, and so it's just wants to find sine and cosine of that. Well, again, sine of beta, cosine of beta. We have our array, our terminal side, and that is still has that point 10, -6, and we have the same radius. So it's the exact same. So even though we're talking about these two different angles, they are coterminal, which means their sine values and cosine values are still going to be the exact same. So then, go back to black, this is going to be negative 6 over root 136, which is approximately negative 0.514. And this is going to be 10 over root 136, which is approximately 0.0, not 0, 8. I think that was just a bad 8 I drew up there. 0.857. Sorry about that. So cosines of both alpha and beta are approximately 0.857. That's it, right? That's not too hard. That's not bad. Okay. And so what's really cool here is if alpha and beta are coterminal angles, right? It doesn't even have to be within one rotation like we had before, just any coterminal angle, then we get that all of their trig functions all match. They're all equivalent. So it makes it really nice and simple. So as long as, so this is provided alpha and beta are in the domain of the respective functions. Yes. And so all that means is things like if we go back up here, right? So we had issues like cosecant of theta is r over y, so y can't equal 0. So if y is 0, that would be like having a 90-degree angle. Would give us a y value of 0. So 90 degrees is not in the domain of cosecant. Okay. So what's really cool about this is we can create these two general statements that sine of alpha is equivalent to the sine of alpha plus 2n pi. And you can also write that 2 pi n, which is actually, I think I'm going to do that because I like that better. So 2 pi n, where n is any integer. Okay, so what this is just saying is, so 2 pi n is just giving us a kind of full rotation. So if n is 0, then we get alpha just being whatever it is. If n is 1, then it's go to where alpha is and then do one full rotation around. If n is negative 1, it's go to alpha and then do one full rotation backwards. And exactly the same for cosine. We get that cosine alpha plus 2 pi n. And both of these, n is any integer. Okay, and that works for all of these values as well. Again, assuming that alpha is within the domain of the respective function. Because if alpha is, then any coterminal angle is as well. So find sine and cosine for 150 degrees. How do we do that? What do we do? Do we just like hope and pray? Well, let's draw out 150 degrees and let's see what we get. Okay, so 150 degrees. So if we start here and we go to here, that's 90. If we go all the way back to the x-axis, it's 180. So we're going to be like about here. This is 150 degrees. If that's 150, what's this? Well, that's going to be 30 degrees, right? Because the two combined are going to give us 180. Okay. So this is going to be really nice. If we think back to a couple lessons ago, and I want you guys to actually go back and look in your notes. I'm going to be that mean, terrible professor and make you guys do this because it's important for you to be able to go back in your notes. Remember when we made that table of special angle values, right? Yes, some of you maybe know. Anybody? Bueller? Right, you guys can't actually answer me, so it's not fair for me to be saying that. So that would be in the last lecture. Right? So in case you guys are still searching, that'd be in the last lecture. We created that table with special triangles. Okay, and so I'm going to refresh you guys. It had sine, cosine, tangent, cosecant, secant, cotangent of different angles, and we had 30 degrees. We had that the sine was 1/2, and that cosine was root 3 over 2. Okay, so when we're looking at this, we still have a 30-degree angle if we think of it like using this right triangle. But the difference here is that the x value is negative. Our y value is positive. And so what does that do? Okay, well, it means when we look at the sine of 150 degrees, and we look at cosine of 150 degrees, if we come back all the way back to the top of this, right? I'm having you guys search through your notes and make you guys do a little research yourself. Sine involves the y value, cosine involves the x. So now if we come back, so sine of 150 is involving the y, and the y is positive here. And so it's still just going to be 1/2, just as it was in the table. But the cosine involves the x value, which our x value for a 150 degree is negative. So instead of it being root 3 over 2, it's going to be negative root 3 over 2. Okay, so I know this is like, wait, how is a 150 the same as a 30? It's not the same, but it is a kind of a similar. We can kind of create this 30-degree angle here that gives us the same kind of sine and cosine that it would over here, except it's using a negative x value. Okay, let's do another example. Okay, so we want to find the sine and cosine of this angle theta here. So what's the first thing we have to do? So we have the point negative 512. The first thing we need to do is we need to find r. So r, using the Pythagorean theorem, is equal to the square root of 12 squared plus negative 5 squared. Now this is slightly the Pythagorean theorem. It's also a distance formula in two-dimensional space. So if you've done this before, and that's all just built off of right triangles. And so if we do this here, we square 12, we square negative 5, what we get is the square root of 144 plus 25, which is the square root of 169, which gives us 13. Look at that. That's really nice. I was nice to you guys, right? Gave you good numbers. So to find sine of theta, that is just y over r. So our y value here is 12. Our r value, 13. To find cosine of theta, that's just x over r. Our x here is negative 5, and our r value is 13. Pretty nice and simple. Okay, so this one here, B, was really pretty easy. It was pretty straightforward to what we've been doing so far this lesson. Part A, you might be like, whoa, what in the world did we do? Right? But what it involves simply is remembering this information here or being able to look it up, right? So recognizing that 150 gives us kind of a corresponding 30-degree angle. So we have the same values. Okay. And this is something we're going to get into a little bit more in a future class that will help us to be able to understand all of this even better. Okay, and so we're going to get into this, into what's called a unit circle, and we'll talk about that, and that will help make things be like, oh, okay. So let's continue on with this example. We're just finding more degrees, more angles. So theta equal negative 3 pi over 4. So let's first figure out where in the heck is negative 3 pi over 4? So this is radians, right? Degrees, we have a little bit more intuition of. If you wanted to, you could convert this in degrees, but that's a waste of time. It's something I want you to get practice understanding radians and stuff like that. So I know that at the x-axis, it's 0 pi, right? At the negative x-axis, it's pi, and back all the way around is 2 pi, okay? We're going negative, so that means we're looking at going counterclockwise. So what we have to think about is, okay, how big is this value? How many pi's are there? Is there one whole pi here, right? Or in this case, a negative pi, right? The negative really just tells us, in this case, with angles, it just tells us whether we're going counterclockwise or clockwise. So the negative tells me we're going counterclockwise. So I need to figure out, do I have a whole pi? Well, if I had a whole pi, that would mean that that I have that ratio there is bigger than 1, but it's not. So 1 whole pi would bring us from the x-axis back to the x-axis. We don't have enough for that. Do we have half a pi? Right? And we do, right? And if you think 3/4 is 0.75, so okay. So that means this angle is going to be right here. So this is negative 3 pi over 4. So how do I figure this angle out? Well, if you wanted to jump into degrees, because that's what our table was, right? So if you found that table from the last lecture, hopefully you can find it again real quick. 45 degrees is what this is mirroring. So this right here is a 45 degree, or pi over 4. The reason why that's important is because it allows us to use these sine and cosine values of a 45 degree angle for this angle here, okay? And so what we know from that is that so sine of 45 degrees is root 2 over 2, and cosine of 45 degrees is root 2 over 2. Cool. Now, what do I do with that? Well, we just think about what these kind of x, y values are. We're in the third quadrant, so that means both our x and our y values are negative, which since sine is y over r and cosine is x over r, these are both going to be negative. So that means that sine of negative 3 pi over 4 is negative root 2 over 2. And cosine of negative 3 pi over 4 is negative root 2 over 2. That's pretty awesome. So what's really nice is you can kind of break up each quadrant having its own 30, 45, and 60 degree angles. And just so here, this would be kind of a 45 degree angle, but in the third quadrant. And so what changes is whether your signs are positive or negative or not. So that's really useful, right? So being able to identify which quadrant the angle falls into, whether it is kind of similar to a 30, a 45, or a 60, that is all really what's helpful. So I want you guys to pause this video and do part D on your own, okay? I want you guys to work through and solve what these sine and cosine values are if alpha is negative 5 pi over 3. So go ahead, pause the video. Keep working. Pause it. Come on, you can do it. All right. Good job. Thank you. So let's look at this angle. The first thing to do is to recognize where this is at. Again, it's radians, okay? But we're not scared of radians. We can think through this. Okay. So negative 5 pi over 3. Is it a full pi? So negative just tells us the direction we're going. So we're going clockwise. So 5/3, that's more than 1 pi, right? So 3 over 3 would be 1 pi. So it's more than 1. Is it more than 3 pi over 2? And this is where it gets a little fuzzy if you're really bad at fractions. And so what we have to ask is kind of what sign? So what sign do we put here? Is 3/2 bigger than 5/3, or is 5/3 bigger than 3/2? And for those of you who are decimal-oriented people, right, you could convert these to decimals actually pretty easily. But we can think of it like this. So 3/2 is 1.5, and 5/3 is 1 2/3. 2/3 is bigger than a half, so that means 5/3 is bigger than 3/2, which means our angle, don't autocorrect to a circle, is this. So this is our -5 pi over 3. Now, what may not be as obvious is kind of what this angle here is. Stop correcting. Let me go a different color. Maybe we'll do it then. This is going to be a 60-degree angle. Okay. So this trig function, so sine of -5 pi over 3 and cosine of -5 pi over 3. What's really cool is because these are in the first quadrant. So this is equal to the sine of 60 degrees, and this is equal to cosine of 60 degrees. And the reason why is because these are coterminal angles. So you can really simply just grab your chart there that we had in last lesson in 6.2, and you can look and see, hey, what is the sine of 60 degrees? What's cosine of 60 degrees? And we get a very simple idea here that this is root 3 over 2, and this is 1/2. Okay. Easy. Hopefully you guys got that as well. For those of you who did not pause the video and try it yourself, shame. Just kidding. But make sure you guys do try and practice these yourselves. These are things that if we were in class, I would be stopping the lecture and walking around the room and making you do these problems. So if I say pause the video and do these problems, try and pause the video and do the problems. All right. For beta equals 22.9 degrees rounded to 4 decimal places. Okay. So we need to figure out sine of 22.9 degrees. And we need to find cosine of 22.9 degrees. Well, that's not a 30, 60, or 45, so we don't have that in that chart. And it's not like 150, so we don't have like that kind of similar to that. So what do we do here? Oh, easy enough. We just use our calculators. So anytime we're saying rounded to 4 decimal places with the trig function, it pretty much exclusively means that you are using your calculator. Now, if I do not tell you to round, try your best to keep it as an exact answer always. Okay? So, making sure our calculator is in the correct mode. This is a very important thing. We need to make sure that we're in degrees. You switch into radians because let's say you want to check these answers with your calculator. Okay, let's actually, let's do that. Let's go back to part D. I want to check this with my calculator. So I'm going to switch the mode into radians. Okay, and I'm just going to do cosine of, now this is where you may want to use some excessive parenthesis usage if you don't have a fraction button within your calculator. So if you have a newer 84, if you hit alpha and then y equals, it may pop up a little menu, and the first option there should say n/d, and that gives you the option to the ability to write in a fraction. If you don't have that, the way I would do this, I'd say cosine, and that's going to give you the COS parenthesis on your calculator. And then I would hit negative parenthesis 5 times pi, close parenthesis, divided by 3, close the cosine parenthesis. But kind of figure it out yourself, work through it. And if you do that with your calculator in radian mode, you get 0.5. All right. So let's go back to this problem here we're working on. Make sure you are in degree mode because this is giving us a value, an angle in degrees. So we just, very simply, once we're in degree mode, we go sine 22.9. We hit enter and we get 0.3891239501. So if we want to round this to 4 decimal places, we would say that this is approximately 0.3891. And then we do the same thing with cosine 22.9 degrees. That's 0.92185 or 11854.056. So that is very simply 0.92185 9, 2, 1, 2. That's it. Very, very simple. So let's move on. The graph of sine. What does that look like? Well, without just grabbing your calculator, you can grab your calculator and just go to y equals sine of x and go. Now, when we're doing this, we want to make sure our tables are right. When we want to graph this, we want to make our mode go into radians. And the reason for that is really a simple one. If we graph it in degree mode, for it to complete kind of one lap around the circle, we'd have to take our x values from 0 all the way up to 360. But if we do it from in radian mode, to get one lap around the circle, we only have to go to 2 pi, which is 6.28 roughly. And so that makes it really easy. Okay. But before we get to our calculators, I want to just create a table. Okay. So let's see here. We'll have our, I don't like t because this is angles. So we'll have our angle theta, not a circle, theta. And then we'll have sine of theta. So let's have our angle go from 0. Let's do pi over 6, pi over 4, pi over 3, pi over 2. Okay. Let's just start there and make our way around. Okay. So 0. So sine of theta, we're at 0. You could definitely grab your calculator and use it, but I'm going to give you a little hint. So 0 is obviously 0 is the same as 0. Pi over 6 is kind of like 30 degrees. Pi over 4 is 45 degrees. Pi over 3 is like 60 degrees. This is like This is like 90 degrees. Okay. So remember, sine is the y value. So if we have our angle in standard position, 0 degrees, our angle is right here. What's that y value? It's 0. So we have 0 over r, which is just 0. Okay. So now using that chart to help us out, okay, sine of pi over 6 is just 1/2. Sine of pi over 4 is root 2 over 2, okay, which is approximately 0.71. Sine of pi over 3, so this is 60 degrees, right? This is root 3 over 2, okay, which that is about 0.87. What about sine of pi over 2? Well, if you think about back to our xy up here that I've got graphed, that means we're on this axis. So it means our y value is the same as the r value, the radius. So if we have y over r, they're the same values. That's just 1. Well, that's cool. Okay, what if we do 2 pi over 3? 2 pi over 3. And then from 2 pi over 3, let's do 5 pi over 6. And let's just jump to pi. So 2 pi over 3, that gives us root 3 over 2. That's kind of like it's 120 degrees. So it's like a 30. And we just said earlier that is approximately 0.87. 5 pi over 6. Okay, that is 1/2. Okay, which You know what that is. What if it's pi? Well, that means we're over here, which means our y value is, oh, that's 0. Hey, we went 0 to 1/2, and then we have pi over 4, which is 0.71, then 0.87, then 1, then 0.87, then 1/2. And the reason why we don't have the 0.71 again is we just didn't do a 3 pi over 4 angle. If we wanted to, we could do that in there. And then we get back to 0. Okay, that's cool. So far, if I look at a graph starting at 0, okay, so it goes up to 1. Okay, and it goes to 1 at pi over 2. So go up there, and it comes back down to 0 at pi. I'm not going to sketch what happens there. What do you think happens after that? Does it go back up? So after this, if I say do 7 pi over 6, is that going to be back to 1/2 or to root 3 over 2? Or what's going to happen there? Well, it's actually going to go to negative 1/2. Okay, and then if we do 4 pi over 3, we get negative root 3 over 2. Okay, this is kind of going crazy. Let's keep going. Let's see 3 pi over 2. 3 pi over 2. Well, 3 pi over 2, that's right down here, right? Because 3 pi over 2 is down there, which means the r and the y value are the same. Oh, but wait, the y value would be negative. So 3 pi over 2 is actually going to give us negative 1. Okay. What about 5 pi over 6? That's like almost all the way around, right? It's also negative root 3 over 2. 11 pi over 6. Or sorry, this is 5 pi over 3. Just use the eraser. 5 pi over 3. 11 pi over 6, that is just giving us a negative 1/2. And then if we did one more, and we got to 2 pi, that's the same as 0, which was 0. So what actually happens is then we get to, here we get to our 3 pi over 2, and then 2 pi. So what this does is it has this kind of cyclical nature like this. Okay, and so this is what happens. Okay. Sorry, daughter interrupted me. And so this is what the trig functions do, especially the sine and cosine function. We're going to draft cosine in just a second. So if you grab your calculator, okay, make sure your mode is in radians. Again, this is just for a simplicity's sake, just to make our windows a lot easier to create. And y equals just its sine of x, and you want to use that button to the right of alpha, right? So it's that kind of second down, second over. It should say xt theta n. That's just our variable button, okay? And so then what you're going to do is you don't want to hit graph from there, depending on what your window looks like, it's going to do all sorts of things. So we want to go to window, and for x value, so it says x min, x max. Well, for x min, we want to do negative 2 pi. For x max, we do 2 pi. For the y, and then x scale, x SCL is our x scale, which is how often we have tick marks. Let's do that at pi over 2. For y max, the maximum value of the sine and cosine function is 1, and the minimum value is negative 1. So let's do, for the max, let's do 1.5, and for the min, let's do negative 1.5, okay? And for the y scale, you can leave it, I just leave it at 1. And once you've got all that, hit graph. And now you can see this graph of the sine function. It's really cool. Okay. Now cosine, we can do all those same values again, but let's just do some really simple ones. Okay. So we have theta, cosine of theta. Okay, so let's just do 0, pi over 2, 3 pi over 2, and 2 pi. The reason I'm doing those is because we know it's going to have the same kind of smooth motion, right? Because we know that sine of alpha is equal to cosine of 90 minus alpha, right? So we have this very similar relationship. What that actually gives us is this 1, 0, negative 1. Oh, I forgot pi in there. There we go. Okay, so for pi, we get negative 1. 3 pi over 2, we get back to 0. And 2 pi back at 1. Okay, and so what our graph ends up looking like is very similar to the sine graph. The difference is, so sine, if we go from 0 to 2 pi, starts at 0, 0, goes up to 1, down to negative 1, back to 0. Cosine starts at 1, down to 0, down to negative 1, and back up like that. So what I've drawn here, so the 0 to 2 pi is what we call one period, okay? And so this is one period of the function. And we're going to talk more about this in section 6.5. We're going to talk about graphing these and some of the terminology and stuff like that with that. Now, tangent function is different. And you can graph that on your calculator and see, but I'm just going to very briefly give you a little sketch of it. I don't really want to go too far into it. Okay. So we'll have negative 3 pi over 2, negative pi over 2, right? So that means negative pi is right here. We'll have pi over 2 and another lovely 3 pi over 2.
Daddy. Dad.
Okay, sorry about that. So what this graph does is at 3 pi over 2 and pi over 2 and negatives and positive, we get asymptotes. And our function between there, let's see if we can draw a little smoother. Looks like this. And so this is what this tangent function looks like. And so it goes through the origin here. This is just my terrible drawing. And what that comes from, if we think back to what tangent is tangent is the y over x. So anytime the x value is 0, it's undefined. So that is what we get going on here. Okay, so those are some rough graphs. We are going to do more graphing with these functions a little later. We're going to talk more about these, but I wanted to give you guys this nice quick visual of what they look like and how they appear and kind of how to get those graphs. So the way we got those graphs here is just by plotting points and figuring that out. We're going to talk all about the things like amplitude, period, phase shift, and stuff like that. Those are terms that we will go over when we talk about how to graph these in more detail. So that's it for this lesson, you guys. See you next time.